Hello there and welcome back to the Science Sleepy Minds. Tonight, you're not in your bed. Well, you are, technically. Your body is there, your pillow is doing its best, and maybe you have a blanket situation that took you a solid 5 minutes to get just right. But your mind is somewhere else entirely. Right now, picture yourself suspended in the blackness of deep space, untethered, weightless, surrounded by a silence so complete you can almost hear your own thoughts echoing off the walls of the cosmos. Somewhere ahead of you, catching the faintest whisper of ancient light, a golden hexagonal mirror the size of a tennis court slowly rotates. That is the James Webb Space Telescope, and what it just found has made some of the smartest people on this planet lose a considerable amount of sleep. Which is ironic, given that you are here specifically to gain some. You probably will not survive this entire script awake, and honestly, that is the highest compliment you can pay me. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Also, drop a comment telling me where you're listening from and what time it is where you are. I always love reading those. Someone is always tuning in from a place I have never heard of at 3 in the morning, and that is beautiful. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're still floating out there, by the way. I didn't forget about you. The cold of space is not really cold in the way you think of cold. There is no wind, no chill against your skin, because there is almost nothing out there to carry temperature at all. It is just absence. An absence so vast that the human brain sort of shrugs and gives up trying to process it. And in that absence, light is travelling. Light that has been travelling for so long that the Earth did not exist when it started its journey. The solar system did not exist. The Milky Way was barely a thought in the gravitational mind of the early universe. This light left its source and just kept going, stretching, reddening, shifting out of the visible spectrum and into the infrared, like a singer whose voice drops lower and lower over billions of years until only the most sensitive ears in the cosmos can still hear it. That is where the James Webb Space Telescope comes in. It was built in the simplest terms to be those ears, or eyes really, a pair of golden eyes tuned not to the light you and I can see, but to the light that has been stretched by the expansion of the universe itself. And for a while, everything it found was spectacular but expected. Gorgeous nebulae, atmospheric compositions of exoplanets, baby stars wrapped in cocoons of gas and dust. Scientists were thrilled. The public was charmed. Everybody was having a great time. And then the telescope looked deeper, farther, back to a time so close to the very beginning of everything that, according to every model physicists had carefully built over the last century, there should not have been much to see. Maybe a few dim clumps of primordial hydrogen, maybe the faintest flickers of the first generation of stars struggling into existence. What the telescope found instead was something that, to put it in the mildest possible terms, did not fit. Galaxies. Fully formed, luminous, complex galaxies filled with billions of stars, sitting in a region of time where they had absolutely no business being. Now, when scientists say something does not fit, it is not like when you say your jeans from 2 years ago do not fit. It is more like opening your front door and finding a skyscraper in your garden that was not there yesterday and that no known engineering could have built overnight. These galaxies were too big, too bright, too structured, too old. And the word that kept creeping into the papers, the word that made cosmologists set down their coffee mugs and stare at their screens a little too long, was impossible. Not improbable, not unlikely. Impossible, given the current understanding of when the universe began and how fast things can form within it. The Big Bang theory, which has been the backbone of modern cosmology for decades, tells a very specific story about the first few 100 million years. It is a story of gradual cooling, slow clumping, and patient accumulation. Hydrogen atoms drift together, gravity nudges them closer, and eventually, after a long and frankly tedious process, the first stars ignite. It is a story with a timeline, and that timeline has rules. You do not get a fully furnished galaxy 300 million years after the universe begins, any more than you get a cathedral 3 hours after someone invents the brick. And yet, there they were, sitting in the data like uninvited guests at a party who somehow arrived before the host. The James Webb Space Telescope, in its quiet, methodical, golden way, had detected something that appeared to be older than the Big Bang itself, and the scientific world, which prides itself on composure and peer review and cautious language, collectively whispered a word that does not often appear in academic journals. That word was what? Just what? Historians of science still argue whether the initial reaction from the astronomical community was genuine shock or the performative kind that academics deploy when they sense a career-defining moment. Either way, the silence that followed was the loudest thing in cosmology in years, and you, lucky you, get to hear the whole story tonight while you drift off to sleep. You're still out there, floating in that immense dark, and the James Webb Space Telescope is turning its golden gaze towards something impossibly far away. But before you chase that ancient light to its source, you need to understand how this machine actually works. Because it is not simply a bigger, shinier Hubble, it is a fundamentally different kind of instrument, and the way it sees the universe is, honestly, one of the most elegant tricks in all of modern science. Think of it this way. You're standing on the shore of an enormous lake at sunset. The sun has already dipped below the horizon, but its light is still bouncing off the water, reaching your eyes in long reddish wavelengths. You're not seeing the sun as it is right now. You're seeing it as it was about 8 minutes ago, because that is how long the light took to travel from there to here. Now stretch that idea. Stretch it so far that the light you're catching did not leave 8 minutes ago, or 8 years ago, but 13 billion years ago. That is what Webb does. It catches light that has been in transit since the universe was practically a newborn, and it translates that light into images and data that tell us what the cosmos looked like back then. The key word in all of this is infrared. You've probably heard the term tossed around in science fiction, or maybe in the context of those thermal cameras that make people look like angry ghosts. Infrared light sits just beyond the red end of the visible spectrum, which means your eyes cannot detect it, but your skin can feel it as heat. When you hold your hands near a campfire and sense the warmth radiating toward you, even though you are not touching the flames, that is infrared radiation. It is everywhere. It is constant, and it turns out it is the secret language of the ancient universe. Here is why. The universe is expanding. It has been expanding since the Big Bang, and it is not just that galaxies are moving apart from each other like boats drifting on a rising tide. Space itself is stretching. The actual fabric of the cosmos is pulling apart at every point, and as it does, the light travelling through it gets stretched too. A photon that started its journey as bright ultraviolet light, the kind that gives you sunburn, gets pulled and elongated over billions of years until it shifts through the visible spectrum, past red and into the infrared. Astronomers call this redshift, and it is one of the most important concepts in all of cosmology. The farther away something is, and the longer its light has been travelling, the more redshifted it becomes. The most distant objects in the universe are so redshifted that their light has been stretched entirely out of the visible range. You could point the most powerful optical telescope ever built directly at them and see absolutely nothing. They are invisible to visible light. They are ghosts, unless you have an instrument that can see in the infrared. Enter Webb. Its primary mirror, that gorgeous honeycomb of 18 gold-coated beryllium segments, is designed specifically to collect infrared light. It is stationed at a point in space called the second Lagrange point, or L2, about 1.5 million kilometers from Earth, which is roughly 4 times the distance to the Moon. It sits there in the gravitational sweet spot between the Earth and the Sun, and it keeps a massive sunshield the size of a tennis court between itself and any source of heat. Because infrared astronomy has a mortal enemy, and that enemy is warmth. Any stray heat from the Sun, from the Earth, even from the telescope's own electronics, would blind the instruments the way a flashlight in your face would blind you in a dark room. The sunshield cools the telescope's instruments to about minus 230 degrees Celsius, which is so cold that if you could somehow stand on the dark side of Webb, the air in your lungs would crystallize before you finished your first surprised gasp. Not that there is air out there, but you get the idea. This extraordinary sensitivity is what allows Webb to do something no other telescope has ever done. It can look back in time to within a few 100 million years of the Big Bang and actually see what was there. Hubble could see far, certainly, but its vision was primarily invisible and near ultraviolet light, which meant the most ancient, most red-shifted objects were beyond its reach. It was like trying to listen to a conversation happening 3 rooms away. You could catch fragments, maybe a word here and there, but the full picture eluded you. Webb, by contrast, has its ear pressed directly against the wall. Scholars still argue whether Hubble or Webb represents the greater leap in astronomical capability, and the answer probably depends on which generation of astronomer you ask. But there is no debate about one thing. Webb sees farther into the past than anything humanity has ever built, and what it sees, when it looks that far back, is not what anyone expected. The universe at 300 million years old was supposed to look like a construction site in its earliest days. Piles of raw material everywhere, maybe a foundation or two being laid, but nothing you could call a finished building. Instead, Webb found skyscrapers. It found galaxies with defined structures, spiral arms, stellar populations that included heavy elements forged only in the hearts of stars that had already lived and died. It found, in essence, a city where there should have been an empty field. And the question that rose from every observatory and university department on Earth was both simple and staggering. How did this get here so fast? Or more unsettlingly, was it here before the beginning? You feel the quiet of space pressing in around you, and the golden mirror of Webb tilts again, catching another ancient photon that has been falling through the dark for longer than the Earth has existed, and you realise that the answer to that question is going to change everything. The photon lands on the mirror and the data streams back to Earth, but to understand why that data is so disturbing, you need to know the story it is supposed to tell. The official story, the one printed in every textbook, taught in every university, and repeated at every scientific conference for the better part of a century. The story of the Big Bang. And like all good stories, it begins with nothing. Not nothing as in an empty room, not nothing as in a blank page, nothing as in the absence of everything. No space, no time, no matter, no energy, no dimensions, no directions, no up, no down, no here, no there. A nothing so complete that the word nothing does not even do it justice, because the concept of a word requires a mind, and there were no minds, and there was no place for minds to be. You're trying to picture it right now, and your brain is doing that thing where it quietly refuses, like a dog sitting down in the middle of a walk and declining to go further. That is perfectly normal. Human brains evolved to track fruit and avoid predators, not to conceptualize the total absence of existence. Give yourself some grace. And then, approximately 13.8 billion years ago, something happened. From that incomprehensible nothing, or from an infinitely dense, infinitely hot point that physicists call a singularity, the universe erupted into being. Not an explosion in space, because there was no space for it to explode into, but an expansion of space itself. Everything that would ever exist, every atom that would one day become a star or a planet or a cup of tea or your left thumb, was compressed into a volume smaller than a proton, and then it was not. It expanded, furiously. In the first fraction of a second, the universe went from subatomic to cosmic, doubling in size again and again in a process called inflation that lasted for a sliver of time so small that writing it as a decimal would require more zeros than you have patience for tonight. After inflation ended, the universe was hot, unimaginably hot, a seething plasma of quarks and gluons and photons, all smashing into each other with energies that no particle accelerator on Earth could ever hope to replicate. It was, for lack of a better term, a mess. But it was an organised mess, governed by the fundamental forces of nature that had crystallised out of the initial chaos like ice forming on the surface of a pond. Gravity was there, electromagnetism was there, the strong and weak nuclear forces were there, and they began doing their work, pulling things together, sorting the chaos into something resembling order. Within the first 3 minutes, and this is one of the most remarkable facts in all of science, the universe had already forged its first atomic nuclei. Hydrogen, mostly, a good amount of helium, a tiny sprinkle of lithium. That is it. That is the entire periodic table for the first few 100 million years. No carbon, no oxygen, no iron, no gold. Nothing heavier than lithium, because heavier elements require the crushing pressures and temperatures found inside stars, and there were no stars yet. The universe was a hot, uniform soup of light elements and radiation, expanding and cooling like breath on a winter morning. For about 380,000 years, this soup was opaque. Photons could not travel freely because they kept slamming into free electrons, scattering in every direction like someone trying to walk through a crowd at a concert. But as the universe cooled below about 3,000 degrees Kelvin, something magical happened. Electrons slowed down enough to be captured by atomic nuclei, forming the first complete atoms in an event called recombination, which is a frankly misleading name since the electrons and nuclei had never been combined before. Physicists are not always great at naming things. Scholars still argue whether recombination or first combination would have been more accurate, and honestly, the debate is more entertaining than it has any right to be. When recombination occurred, the universe became transparent. Photons were suddenly free to travel unimpeded, and they did, streaming out in every direction in a burst of light that has been travelling ever since. That light, now cooled and stretched by 13.8 billion years of cosmic expansion, is what we detect today as the cosmic microwave background radiation, or CMB. It is the oldest light in the universe, a snapshot of the cosmos when it was just 380,000 years old, and it is everywhere. About 1% of the static on an old analog television that has lost its signal is actually CMB radiation. You've been watching the afterglow of creation your entire life and did not know it. There is a quirky bit of history here too. The CMB was discovered accidentally in 1965 by Arno Penzias and Robert Wilson, 2 radio astronomers in New Jersey, who initially thought the persistent background hiss in their antenna was caused by pigeon droppings. They spent weeks cleaning the antenna and evicting pigeons before realizing they had stumbled upon the most important cosmological discovery of the 20th century. They won the Nobel Prize. The pigeons did not. After the CMB was released, the universe entered what astronomers poetically call the Dark Ages. No stars, no galaxies, just vast clouds of hydrogen and helium drifting in an expanding darkness, slowly being drawn together by gravity. The first stars, the so-called population 3 stars, are believed to have formed somewhere between 100 and 200 million years after the Big Bang. They would have been enormous, hundreds of times the mass of our Sun, burning hot and bright and fast, living short, violent lives before exploding as supernovae and scattering the first heavy elements into the void. Those heavy elements would seed the next generation of stars and the next, and eventually, billions of years later, you. That is the story. Neat, sequential, logical. Nothing exists before the bang. Everything builds gradually afterward, and for decades, every observation confirmed it. Until Webb looked back and found something waiting in the dark that should not have been there. You can almost feel the moment it happened, even though you were not in any of the control rooms or research labs where the data first appeared on screen. It arrived quietly, the way most revolutions do, not with a dramatic press conference or a breathless breaking news banner, but with a graduate student frowning at a monitor, adjusting parameters, running the calibration again, and then leaning back in a chair with the particular expression of someone who has just realised that either their software is broken or the universe is. The James Webb Space Telescope had begun its deep field observations, which is a fancy way of saying it pointed at a tiny, seemingly empty patch of sky and stared at it for a very long time. This is the same technique Hubble used to produce its famous deep field images back in the mid-1990s, when it revealed that what appeared to be a blank square of darkness actually contained thousands of galaxies, each one home to hundreds of billions of stars. That image changed humanity's understanding of the universe more profoundly than almost anything before or since, and the only reason it is not talked about more is that most people saw it, said, "Huh, neat," and went back to watching television. Historians still argue whether the Hubble Deep Field or the Apollo 8 Earthrise photo had more impact on public consciousness, but in scientific terms the deep field was a seismic event. Webb's deep field observations were supposed to build on Hubble's legacy. Same concept, vastly better instrument, and the initial results were everything astronomers had hoped for. Galaxies upon galaxies, stacked in layers of cosmic time, each one more distant and more ancient than the last, their light reddened by billions of years of expansion. The images were breathtaking. They were also, at first, entirely consistent with the standard model. Here were the young galaxies of the early universe, small and irregular, still assembling themselves from the raw materials left over after the Big Bang. Everything made sense, and then the software flagged something. Deep in the data, among the thousands of faint red smudges that represented the most distant objects ever observed, a handful of sources stood out. Their brightness was wrong. Not wrong in the sense of being too dim, which you might expect from objects at the edge of the observable universe, but wrong in the sense of being too bright, significantly too bright, and their spectral profiles, the fingerprints of light that tell astronomers what an object is made of and how far away it is, suggested redshifts so extreme that these objects would have to exist within the first 300 to 500 million years after the Big Bang. That alone was remarkable. But the real problem was not their distance, it was their size. These were not the small, chaotic proto-galaxies that the models predicted for that era. These were massive systems, containing tens of billions of solar masses worth of stars, arranged in structures that bore an unsettling resemblance to galaxies you might find in the much more recent universe. Some showed hints of spiral arms, others appeared to have well-defined cores surrounded by extended halos of older stars. One research team described finding a galaxy with a stellar population that appeared to include red giant stars, which are stars that have already exhausted the hydrogen fuel in their cores and expanded into their twilight phase. Red giants take time to develop. A lot of time. More time, in some cases, than the age of the universe would have permitted at the point when this galaxy apparently existed. You're lying in the dark and that fact is settling over you like a second blanket. These galaxies should not have been there. They should not have been that big. They should not have been that complex, and they definitely should not have contained stars that were already old. It was as if someone had dug into the deepest, oldest layer of an archaeological site, the layer where you expect to find nothing but bare soil and maybe some microorganisms, and instead pulled out a fully functioning smartphone. The thing is not just unexpected, it is categorically incompatible with the established timeline. The research teams did what good scientists always do when confronted with impossible data. They checked their work, they recalibrated the instruments, they ran the photometric analysis again with different assumptions, they consulted colleagues at other institutions who were working with independent datasets, and one by one, the checks came back confirming what the original data had shown. These objects were real, their redshifts were accurate, their masses were not an artifact of some systematic error in the pipeline. The galaxies were genuinely there, genuinely ancient and genuinely too large and too mature for the universe they inhabited. Papers began to appear, cautiously at first, with titles that used words like candidate and tentative and if confirmed. That is the academic equivalent of screaming. When a scientist uses the phrase if confirmed, this result would challenge our current understanding. What they actually mean is, I believe we've found something that breaks the model, and I am terrified and exhilarated in equal measure, but I need to sound calm because my tenure review is next month. The astronomical community, to its credit, responded with a mixture of rigour and genuine curiosity. Nobody was dismissing the findings outright. But nobody was ready to throw away the Big Bang model either. Not yet, not without more data. The problem was that more data kept arriving, and every new batch made the mystery deeper. Webb was not finding one or two anomalous objects, it was finding dozens, then scores. The early universe, it seemed, was far busier and far more mature than anyone had imagined. And somewhere in the growing pile of impossible galaxies, a question was forming that nobody quite wanted to ask out loud, because asking it would mean contemplating the possibility that the origin story of the universe, the story you just heard a few minutes ago, might be incomplete, or worse, might be wrong. The galaxy that cracked the door wide open had a name that only an astronomer could love: JADES-GS-Z 14-0. No poetry in it, no grandeur, just a string of letters and numbers that sounds like a printer model, or maybe a particularly dull password. But behind that clinical label sat an object so extraordinary that it rewrote the record books and kept rewriting them until the books gave up and asked for new pages. JADE stands for the JWST Advanced Deep Extragalactic Survey, which was one of the major observation programs designed to use Webb's infrared eyes to probe the farthest reaches of the cosmos. The survey targeted a well-studied patch of sky in the constellation Fornax, a region that Hubble had already examined extensively. Astronomers knew this territory. They had mapped it, catalogued its contents, and felt reasonably confident about what was there. Webb was supposed to refine the picture, add detail, maybe push the boundary of the known universe back by a few 100 million years. It was supposed to be an incremental advance. What it delivered instead was a revolution in a data file. JADES GSZ 14.0 appeared in the data with a spectroscopic redshift of approximately 14.32, which, when you convert that number into look-back time, places this galaxy at roughly 290 million years after the Big Bang. Let that settle in for a moment. The universe is 13.8 billion years old. This galaxy existed when the cosmos was about 2% of its current age. If the entire history of the universe were compressed into a single calendar year, with the Big Bang at midnight on January 1st and the present day at midnight on December 31st, this galaxy would have been shining by January 7th. The Earth would not form until September. Dinosaurs would not appear until Christmas Day. All of recorded human history would fit into the last few seconds before midnight on New Year's Eve. and here was a galaxy, blazing away in the first week, fully assembled, luminous, and utterly defiant of every prediction. The brightness alone was staggering. JADES-GS-Z 14-0 was not a faint whisper of ancient light. It was, for its era, remarkably luminous, which meant it contained a substantial population of stars actively burning through their fuel. The spectral data confirmed the presence of ultraviolet light being emitted by hot, young stars, but also longer wavelength emission that hinted at dust. Dust is important. Dust, in astronomical terms, is made of heavier elements, the kind forged inside stars and scattered into space when those stars explode. You do not get dust without stars, and you do not get the kind of dust Webb was detecting without multiple generations of stars living, dying, and seeding the cosmos with their remains. One generation of stars is not enough. You need cycles: birth, death, enrichment, rebirth, and each cycle takes time. This is where the math starts to feel personally offensive. Population 3 stars, the first stars that ever existed, are theorized to have formed around 100 to 200 million years after the Big Bang. They burned for perhaps 2 to 3 million years before exploding. Their remnants would have enriched the surrounding gas with the first heavy elements, allowing a second generation of stars to form. That second generation would need to live and die as well, before enough dust and metals accumulated to produce the kind of spectral signatures Webb was seeing in JADES GSZ 14-0. Even under the most generous assumptions, with the most efficient star formation rates imaginable, the timeline is agonizingly tight. Some researchers argued it was not just tight, but physically impossible. You cannot squeeze that many generations of stellar evolution into 290 million years. It is like being asked to grow an oak tree in a weekend. You can water it all you want. Biology does not care about your schedule, and JADES-GS-Z 14-0 was not small. Its estimated stellar mass suggested billions of solar masses worth of stars organized into a structure that extended across more than 1,600 light-years. For context, the Milky Way is about 100,000 light-years across, so this ancient galaxy was modest by modern standards, but for something existing in the cosmic dawn, it was enormous. A quirky detail that delighted and baffled researchers was the detection of what appeared to be ionized oxygen emission in the galaxy's spectrum. Oxygen, the third most abundant element in the universe today, but one that requires stellar nucleosynthesis to produce. Finding oxygen at a redshift of 14 is like finding a handwritten letter in a cave that predates the invention of writing. It implies a history that the timeline does not support. The discovery team, led by researchers from institutions across the United States and Europe, published their findings with the measured caution that the situation demanded, but the undercurrent of astonishment was unmistakable. Scholars still argue whether JADES-GSZ 14-0 alone is sufficient to challenge the standard cosmological model, or whether it merely represents an extreme outlier that future refinements in galaxy formation theory will eventually accommodate. The optimists say the models can be stretched. The pessimists, or perhaps the realists, say the models are already stretched to breaking. And the telescope, indifferent to human debate, continued its survey, its golden mirror patiently gathering more ancient photons, each one carrying a piece of a story that was getting harder and harder to reconcile with the neat, sequential, comfortable narrative of a universe that began 13.8 billion years ago and built everything from scratch. You lie still and think about oxygen atoms forged in stars that should not yet have existed, drifting through a galaxy that should not yet have formed, in a universe that was barely old enough to have cooled down from its own birth. And you wonder, not for the last time tonight, what else might be out there that the textbooks have not prepared you for. The thing about one impossible galaxy is that you can explain it away. You can call it an outlier, a statistical fluke, a calibration error that slipped through the cracks. Scientists are trained to be skeptical of extraordinary claims, and a single anomalous data point, no matter how dramatic, does not topple a theory that has been tested and refined for nearly a century. One weird galaxy is a puzzle. It is a conversation at a conference. It is an interesting footnote in a review paper. What you cannot explain away quite so easily is dozens of them. Because JADES-GS-Z14-0 was not alone, not even close. As Webb continued its deep field surveys throughout its first and second years of operation, the catalogue of impossible early galaxies grew with a persistence that shifted the mood in the astronomical community, from curiosity to something closer to unease. Each new observing cycle produced more candidates, more objects sitting at extreme redshifts with masses and luminosities that defied the standard timeline. The names piled up in the databases like evidence in a case that nobody had wanted to prosecute. CEERS-93316, GLASS-Z12, JADES-GS-Z13-0, each one a tiny rebellion against the established order of cosmic history. Some of these galaxies were found in the SEERS survey, the Cosmic Evolution Early Release Science program, which targeted a strip of sky in the constellation Bootes. Others turned up in the GLASS survey, which used gravitational lensing from massive galaxy clusters to magnify the light of even more distant objects behind them. Gravitational lensing is one of those concepts that sounds like science fiction, but is actually one of the most elegant confirmations of Einstein's general theory of relativity. A massive object, like a galaxy cluster, warps the fabric of space-time around it, and light passing through that warped region gets bent and magnified, like looking through a cosmic magnifying glass. Webb used these natural lenses to peer even deeper into the past, and what it found through those lenses was more of the same. Mature galaxies, massive galaxies. Galaxies that looked like they'd been around for a very long time, occupying a slice of cosmic history where very little should have existed at all. The numbers were becoming difficult to reconcile. Early estimates suggested that the stellar mass density of the universe, at redshifts above 10, which corresponds to the first 400 million years or so, was anywhere from 2 to 10 times higher than what the standard Lambda CDM model predicted. Lambda CDM, for the uninitiated, is the reigning cosmological model, the one that incorporates dark matter and dark energy and describes how the universe evolved from the Big Bang to the present day. It has been spectacularly successful at explaining large-scale structure, the distribution of galaxies, the properties of the CMB, and a host of other observations. It is the closest thing cosmology has to a consensus framework, and Webb was poking holes in it with the quiet efficiency of a moth working through a wool sweater. The problem was not just that individual galaxies were too massive, it was the sheer abundance of them. The models predicted that the early universe should have been a sparse, lonely place, with only a handful of small, feeble proto-galaxies struggling into existence in the densest pockets of dark matter. Instead, Webb was revealing a cosmic landscape that was rich, populated, and surprisingly active. Star formation rates in some of these early galaxies appeared to be extraordinarily high, as if the universe had been in a desperate rush to build everything at once. One team calculated that certain galaxies at redshift 12 were forming stars at rates hundreds of times higher than the Milky Way does today. That is not a minor discrepancy. That is a different universe than the one the models describe. A particularly unsettling detail emerged when researchers began looking at the morphologies of these galaxies, which is the fancy term for their shapes. At very high redshifts, you expect galaxies to be irregular, blobby, chaotic. They should look like construction sites, messy and unfinished, because they have not had time to settle into the elegant spirals and ellipticals that dominate the more recent universe. Some of Webb's early galaxies did look like that, which was reassuring, but others did not. Others showed surprisingly smooth light profiles, compact cores, and extended structures that suggested they had already undergone significant dynamical evolution. One research group identified what appeared to be a disk galaxy at a redshift above 10, which is the astronomical equivalent of finding a Swiss watch in a Bronze Age burial site. Disk galaxies require time to form. They require gas to settle into a rotating plane, stars to organize into coherent orbits, and the whole system to reach a kind of gravitational equilibrium that simply cannot happen overnight, even on cosmic timescales. Scholars still argue whether these morphological classifications are reliable at such extreme distances, where the data is sparse and the images are smeared by the limits of even Webb's extraordinary resolution. Some researchers caution that what looks like a disk could be an artifact of how the light is distributed across just a few pixels. Others counter that the spectral data supports the structural interpretation and that the sheer number of candidates makes systematic error an increasingly unlikely explanation. The debate is fierce, collegial, and ongoing, which is exactly how science is supposed to work when it encounters something that threatens to redraw the map. And you, nestled in your blankets, are beginning to sense the shape of the problem. It is not one galaxy. It is not a dozen. It is a pattern, a persistent, growing, undeniable pattern of objects that exist in the wrong place at the wrong time, and the neat timeline of the Big Bang, that beautiful sequential story of nothing becoming everything, is straining under the weight of what Webb keeps finding in the dark. So now you are lying there with a reasonable question forming in the back of your mind, the kind of question that feels simple but unravels into something enormous the moment you pull at it. If these galaxies are real, and the evidence is piling up that they are, then where did all that stuff come from? Not just the galaxies themselves, but the material inside them. The stars, the dust, the heavy elements, the oxygen, remember, that oxygen from a few minutes ago that had no business being there. Because the universe does not just hand you a galaxy fully stocked with complex chemistry. You have to build it, element by element, generation by generation, and that process has rules that even the most creative theorists cannot simply wave away. Let us talk about stellar mass budgets, because this is where the problem goes from puzzling to genuinely alarming. A stellar mass budget is exactly what it sounds like. It is an accounting of how much stellar material should exist at a given point in cosmic history, based on how much raw gas was available, how efficiently that gas could collapse into stars, and how long those stars had to live, die, and recycle their material back into the cosmos. Think of it as a financial ledger for the universe. You start with a certain amount of capital, which is the primordial hydrogen and helium left over from the Big Bang, and you invest it into stars. Each star burns through its fuel at a rate determined by its mass, and when it dies, it returns some of that material to the interstellar medium, enriched with heavier elements. The next generation of stars forms from this enriched material, and the cycle continues. The Standard Model predicts how this ledger should look at every epoch in cosmic history. In the very early universe, the budget is tight. You have plenty of raw hydrogen and helium, sure, but the processes that convert that gas into stars are slow and inefficient. Dark matter halos, the invisible gravitational scaffolding around which galaxies form, need time to grow large enough to pull in sufficient gas. The gas itself needs to cool, which in the absence of heavy elements is a sluggish process because hydrogen and helium are terrible at radiating away heat. Everything conspires to make early star formation a patient, gradual affair. The models predict modest amounts of stellar mass at high redshifts, growing steadily over hundreds of millions of years as the halos get bigger and the gas gets cooler and the feedback loops between star formation and gas enrichment slowly ramp up. What Webb found blew past those predictions like they were suggestions rather than physical constraints. The stellar masses inferred for some of these early galaxies exceeded the total amount of matter that should have been available in their host dark matter halos, even under the most optimistic assumptions about star formation efficiency. This is not a subtle discrepancy. This is like checking your bank account and finding 10 times more money than your salary could possibly explain. Either you have a secret benefactor, or the accounting system is fundamentally flawed. Star formation efficiency is a critical variable here, and it is worth lingering on because it illustrates just how boxed in the theorists are. In the local universe, the efficiency with which gas converts into stars is actually quite low, typically around 10 to 20% in most galaxies. A lot of gas just sits around doing nothing, held up by turbulence, magnetic fields, radiation pressure from nearby stars, and a dozen other processes that collectively act as brakes on gravitational collapse. To explain the masses Webb is seeing at high redshifts, you would need star formation efficiencies of 50, 60, even 100% in some cases. 100% efficiency means every single atom of available gas gets converted into stars with no waste, no leftover material, no gas remaining to form future generations. That has never been observed anywhere in the universe at any time. It is, as far as current physics can tell, not just unlikely but borderline impossible, because the very act of forming stars generates feedback, radiation, and stellar winds and supernovae that blows away surrounding gas and prevents it from collapsing. Stars literally sabotage their own formation process. It is one of the great self-regulating mechanisms of the cosmos, and it is very hard to turn off. A quirky wrinkle in all of this involves the role of supermassive black holes. Some theorists have proposed that the early galaxies Webb is seeing might not be as star-heavy as they appear. Instead, part of their luminosity could come from active galactic nuclei, supermassive black holes at their centers devouring gas and radiating enormous amounts of energy in the process. This would reduce the inferred stellar masses somewhat, but it creates its own problem, which you will hear about later tonight, because those black holes are also far too large for their age. It is problems all the way down. Scholars still argue whether the stellar mass budget crisis is truly as severe as the early analyses suggest. Some researchers point out that the methods used to estimate stellar masses from photometric data involve significant uncertainties, particularly at extreme redshifts where the available wavelength coverage is limited, and the models used to fit the spectral energy distributions are being extrapolated far beyond their calibrated range. Others counter that even the most conservative estimates still exceed the predictions by uncomfortable margins, and that the systematic trend across multiple independent surveys makes it very difficult to dismiss the results as mere measurement error. You breathe slowly in the dark and imagine a cosmic accountant somewhere, hunched over an infinite spreadsheet, discovering that the numbers simply do not add up, that the universe spent more than it had before it should have had anything to spend at all. And so the question that nobody wanted to ask out loud finally starts being asked out loud, first in whispered conversations at conference coffee breaks, then in speculative paragraphs buried in the discussion sections of otherwise cautious papers, and eventually in bold font headlines that would have seemed absurd just 5 years ago. Could stars, or something like stars, have formed before the Big Bang? Now, before you let that sentence carry you off a cliff, let us be careful with it, because before the Big Bang is a phrase that sounds straightforward, but is actually a minefield of conceptual traps. In the standard model, asking what happened before the Big Bang is a bit like asking what is north of the North Pole. Time itself began with the Big Bang. There is no before, because there was no time in which a before could exist. The question is not just unanswered, it is, according to the classical framework, meaningless. Stephen Hawking was particularly fond of making this point, usually with the kind of serene confidence that only a man who had spent decades thinking about the origin of time could muster. But here is the thing about frameworks. They are tools, not truths. They are the best models we have until we get better ones, and the history of science is essentially a long story about frameworks that worked beautifully right up until the moment they did not. Newtonian gravity worked perfectly for 2 centuries, until Mercury's orbit refused to cooperate and Einstein had to step in with general relativity. The steady-state model of the universe, which held that the cosmos had always existed in roughly its current form, was the dominant cosmological theory until the discovery of the CMB in 1965 blew it to pieces in an afternoon. Frameworks are not sacred. They are scaffolding, and sometimes the building outgrows them. The idea that stellar processes might predate the Big Bang is not a mainstream position. Let that be very clear. It sits on the speculative fringe of theoretical cosmology, in that exciting and slightly dangerous neighbourhood where legitimate physics meets radical imagination. But it is not coming from crackpots. It is coming from serious researchers grappling with data that refuses to fit inside the existing box. And when serious researchers start grappling, interesting things tend to happen. One avenue of speculation involves the concept of a pre-Big Bang phase of the universe, a period of existence that preceded the hot, dense state we traditionally call the beginning. Several theoretical frameworks allow for such a phase, and some of them predict that physical processes, including the formation of structures, could have occurred during it. If the Big Bang was not the absolute beginning of everything, but rather a transition, a violent reshuffling of a cosmos that already existed in some form, then the structures Webb is detecting might not be impossibly young. They might be impossibly old. They might be remnants of whatever came before, carried through the transition like fossils preserved in rock that has been heated and compressed but not entirely destroyed. This is a staggering idea, and it deserves to be treated with both excitement and caution in equal measure. The analogy that some physicists use is that of a palimpsest, one of those medieval manuscripts where the original text was scraped off and written over, but traces of the earlier writing remain faintly visible beneath the new layer. If the Big Bang was a cosmic palimpsest, then Webb might be detecting the ghostly traces of a previous text, a previous universe, a previous epoch of star formation and galaxy building that was mostly but not entirely erased by the cataclysm of the Bang. Historians still argue whether the idea of a cyclic or eternal universe is genuinely new or simply a modern rediscovery of ancient philosophical intuitions. Hindu cosmology, for example, has long described the universe as undergoing endless cycles of creation and destruction, with each cycle lasting billions of years. The ancient Greeks debated eternal recurrence. Even in Western science, the oscillating universe model, in which the cosmos expands and then contracts in an endless series of big bangs and big crunches, was a respectable hypothesis for much of the 20th century, before being sidelined by the discovery that the expansion of the universe is accelerating rather than slowing down. The idea that our Big Bang might not be the first or only one has deep roots, and Webb's impossible galaxies are giving those roots new water. A quirky historical footnote here is that Georges Lemaitre, the Belgian priest and physicist who first proposed what would become the Big Bang theory in the late 1920s, was himself open to the possibility that the initial singularity might not represent an absolute beginning. He described it as the cosmic egg from which the universe hatched, and he was careful to note that physics could describe what happened after the egg cracked open, but had very little to say about what, if anything, existed before. Lemaitre understood, perhaps better than many of his successors, that the boundary of the model is not the same as the boundary of reality, so you lie there, feeling the weight of that distinction, the difference between the edge of what we can currently describe and the edge of what actually exists. And you realise that Webb may have pushed past the first boundary and bumped against the second, and the galaxies it found in that gap, those massive, luminous, chemically enriched impossibilities, might be whispering a story that is older than the origin story we thought we knew. The whisper has a name, and it belongs to a man who has spent the better part of his career listening for exactly this kind of signal. Sir Roger Penrose, the British mathematician and physicist who shared the 2020 Nobel Prize for his work on black holes, has been quietly and persistently arguing for decades that the Big Bang was not the beginning. It was a doorway, and what lies on the other side of that doorway is not nothing, not the blank void of non-existence that the Standard Model implies, but another universe, a previous one, an entire cosmos that lived and died, and in its dying gave birth to ours. Penrose's theory is called conformal cyclic cosmology, or CCC, and it is one of the most elegant and unsettling ideas in modern physics. The basic concept, stripped of its considerable mathematical machinery, goes something like this. The universe begins with a Big Bang, expands, forms stars and galaxies, and eventually over trillions upon trillions of years reaches a state of maximum entropy. All the stars burn out, all the black holes evaporate through Hawking radiation, all the matter decays or is swallowed. What remains is an unimaginably vast, cold, empty expanse, filled with nothing but the faintest residual radiation, thinned out to almost zero energy, drifting through a space that has expanded to incomprehensible proportions. This sounds like the ultimate dead end, the heat death of the universe, the final chapter, the last page of the last book in the cosmic library. But Penrose noticed something peculiar about this state, something that depends on a deep mathematical property of space-time. When the universe is completely empty of massive particles, when there is nothing left that has rest mass, the concept of scale becomes meaningless. A photon, which has no rest mass, does not experience time or distance in the way that massive particles do. For a photon, there is no difference between an infinitely large universe and an infinitely small one. The geometry of space-time in this far future state becomes conformally equivalent to the geometry of the initial singularity. In plain language, the end looks like the beginning. The dying breath of one universe becomes, through a mathematical transformation, the Big Bang of the next. Penrose calls each cycle an aeon. Our universe is one aeon in an infinite sequence. The Big Bang that started our cosmos was the conformal boundary between our aeon and the one that preceded it. And crucially, information from the previous aeon can leak through that boundary. Not all of it. Not in a form that is easy to read, but enough, Penrose argues, to leave detectable traces in the structure of our universe. The specific traces he predicted are what he calls Hawking points. In the previous aeon, supermassive black holes would have been among the last objects to evaporate, and as they did, they would have released enormous amounts of energy in the form of Hawking radiation. That energy, concentrated in specific locations, would have punched through the conformal boundary and left subtle warm spots in the cosmic microwave background of our universe. Not hot spots, not dramatic flares, but gentle, circular regions of slightly elevated temperature, barely distinguishable from the random fluctuations that fill the CMB. Penrose and his collaborators have published analyses claiming to have found exactly these features in data from the Planck satellite, which mapped the CMB with extraordinary precision. They identified multiple candidate Hawking points, circular patterns in the CMB temperature map that they argue are statistically significant and consistent with the CCC prediction. This is where the scientific community gets divided, and the division is as much about philosophy as it is about data. Some statisticians have challenged Penrose's analysis, arguing that the patterns he identifies are consistent with random noise and do not require an exotic explanation. Others have supported his methods and found the results compelling. Scholars still argue whether Hawking points represent genuine evidence of a pre-Big Bang universe, or an example of the human tendency to find patterns in randomness, the same cognitive bias that makes you see faces in clouds and hear words in white noise. The debate has been running for over a decade and shows no signs of resolution, which, depending on your temperament, is either frustrating or thrilling. What Webb adds to this picture is circumstantial but provocative. If the previous aeon contained galaxies and stars and black holes, as CCC implies, then the transition between aeons might not have been perfectly clean. Some imprint of those structures, some residual influence on the distribution of matter and energy in the early stages of our aeon, might have persisted. The impossible galaxies Webb is detecting, those massive mature systems that seem to have appeared fully formed in the cosmic dawn, could conceivably be regions where the gravitational legacy of the previous aeon accelerated the formation of structure in ours. Not carried over galaxies in any literal sense, but echoes, gravitational memories, places where the new universe remembers, faintly, what the old universe looked like. A quirky detail about Penrose himself is that he has always been something of an intellectual contrarian, cheerfully willing to defend positions that most of his peers consider outlandish. He has argued that consciousness is fundamentally linked to quantum gravity, a view that most neuroscientists and physicists politely reject. He has challenged the foundations of string theory with a persistence that borders on sport. And he proposed CCC at a time when the cyclic universe concept was deeply unfashionable, publishing his ideas with the calm assurance of someone who's been right before when everyone else was wrong and is perfectly prepared to wait for the evidence to catch up. You lie still and think about eons, about universes ending and beginning and ending again, and the darkness around you feels a little different now, not empty but layered, as if the space between you and the ceiling holds the faintest residue of a cosmos that was here before yours and will be here after it is gone. Penrose is not the only one who thinks the Big Bang might have been a transition rather than a true beginning. There is another family of theories, less poetic perhaps, but no less radical, that approach the problem from a completely different direction. These are the bouncing cosmologies, and they suggest that our universe did not explode out of nothing, but rather bounce back from a previous state of collapse, like a ball that has been squeezed to its smallest possible size and then springs outward again. The most developed version of this idea comes from loop quantum gravity, which is one of the leading candidates for a theory of quantum gravity, the long-sought framework that would unify Einstein's general relativity with quantum mechanics. General relativity describes gravity as the curvature of space-time and works beautifully at large scales. Quantum mechanics describes the behavior of particles at the smaller scales and works beautifully there. But when you try to apply both simultaneously, as you must when dealing with the extreme conditions of the Big Bang singularity, the math breaks down spectacularly. Infinities appear. Predictions become nonsensical. The equations, which have been so reliable everywhere else, simply stop working, like a calculator that displays error and refuses to go further. Loop quantum gravity proposes a solution by suggesting that space-time itself is not smooth and continuous, as general relativity assumes, but is woven from tiny discrete units at the Planck scale, the smallest meaningful length in physics, about 10 to the minus 35 meters. At this scale, space has a granular structure, like a fabric made of incredibly fine threads. And this granularity has a profound consequence. It prevents the singularity. When you run the equations of loop quantum gravity backward toward the Big Bang, the universe does not collapse to a point of infinite density. Instead, it reaches a minimum size, a quantum floor below which it cannot shrink, and then it bounces. The contraction of a previous universe becomes the expansion of a new one, and the Big Bang is reimagined as the Big Bounce. This is not just mathematical speculation. Loop quantum cosmology, the application of loop quantum gravity to the universe as a whole, has been developed in considerable detail over the past 2 decades, and its predictions are specific enough to be tested, at least in principle. The theory predicts subtle differences in the pattern of fluctuations in the cosmic microwave background, differences that arise because the quantum bounce leaves a slightly different imprint on the primordial perturbations than the classical Big Bang singularity would. The differences are small, tantalizingly close to the limits of current observational sensitivity, and detecting them would require the next generation of CMB experiments. But they are there, lurking in the math, waiting to be confirmed or refuted. The implications for Webb's impossible galaxies are significant. If the universe did not begin from a singularity but bounced from a prior contraction phase, then there was time before the bounce. Potentially a great deal of time, an entire universe worth of time, during which stars formed, galaxies assembled, heavy elements were forged, and all the complex astrophysical processes that we observe in our universe played out in a previous one. The bounce would have been violent, certainly. Temperatures and densities would have reached extraordinary levels. But if some fraction of the structures from the pre-bounce universe survived the transition, even in a degraded or partial form, they could have seeded the rapid formation of galaxies in the post-bounce universe. The impossible galaxies would not be impossible at all. They would be expected. Another bouncing model that deserves a mention here is the ekpyrotic scenario, which comes from string theory rather than loop quantum gravity. The name comes from the ancient Greek word ekpyrosis, meaning conflagration, which the Stoic philosophers used to describe their belief that the universe periodically destroys itself in fire before being reborn. Historians still argue whether the Stoics were engaging in genuine cosmological speculation or simply expressing a philosophical preference for cyclical time, but either way, the modern ekpyrotic model borrows their dramatic flair. In this scenario, our universe is a 3-dimensional membrane, or brane, floating in a higher dimensional space. Periodically, our brane collides with another brane, and the energy of that collision manifests as the hot, dense state we call the Big Bang. The collision is not the beginning of everything. It is just the latest in a potentially infinite series of collisions, each one producing a new cycle of cosmic expansion and evolution. A quirky aspect of the ekpyrotic model is that it was partly motivated by a desire to solve problems with the inflationary paradigm, which is the standard explanation for why the universe appears so uniform on large scales. Inflation proposes that the universe underwent a brief period of exponentially rapid expansion in its earliest moments, smoothing out any irregularities. The ekpyrotic model achieves the same smoothing through the slow contraction that precedes each collision, arguing that the pre-bounce phase naturally produces the uniformity that inflation was invoked to explain. It is a completely different mechanism arriving at the same result, which is either deeply suspicious or deeply suggestive depending on your perspective. You're sinking deeper into the mattress now, and the idea of the universe bouncing, contracting and expanding like a slow cosmic heartbeat has a rhythm to it that feels almost soothing. Each bounce a new beginning, each contraction not an end but a preparation. And somewhere in the space between bounces, the raw material for impossible galaxies waiting patiently to spring into existence the moment the cosmos exhales again. The bouncing universe and Penrose's cycling aeons both offer frameworks in which something could exist before the Big Bang. But there is another piece of evidence that has been sitting in plain sight for decades, quietly refusing to behave itself. The cosmic microwave background, that ancient afterglow you heard about earlier, the one discovered thanks to some unfortunate pigeons in New Jersey, is not as perfect as it was supposed to be, and its imperfections are starting to look less like random noise and more like clues. The CMB is often described as the most perfect blackbody spectrum ever measured, and that is true. Its temperature is remarkably uniform across the entire sky, hovering at about 2.725 degrees Kelvin, with variations of only a few parts in 100,000. Those tiny variations, mapped with exquisite precision by satellites like COBE, DUMAP and Planck, are the seeds from which all cosmic structure eventually grew. Slightly denser regions in the primordial plasma attracted more matter through gravity, becoming the galaxies and galaxy clusters we see today. Slightly less dense regions became the vast voids between them. The pattern of these fluctuations matches the predictions of the Standard Model with remarkable accuracy, which is one of the strongest pieces of evidence in favour of the Big Bang and inflation. But within that stunning agreement there are anomalies, features that do not fit, whispers in the data that have been noted, catalogued, debated, and never fully explained. And in the context of Webb's impossible galaxies, they are suddenly getting a lot more attention. The most famous of these anomalies is the CMB cold spot, a region in the southern sky in the direction of the constellation Eridanus that is significantly colder than the surrounding background. It spans about 5 degrees on the sky, which is roughly 10 times the apparent diameter of the full moon, and its temperature is depressed by about 70 millionths of a degree compared to the average. That sounds absurdly small, and it is, but in the context of CMB analysis, where the entire science depends on measuring these minuscule fluctuations with extraordinary precision, it is a significant outlier. The probability of such a large, cold region arising by chance in the Standard Model is estimated to be less than 2%. Not impossible, but uncomfortable. The kind of unlikely that makes statisticians shift in their seats. Several explanations have been proposed for the cold spot. The most conventional is that it is simply a rare but natural fluctuation, the cosmic equivalent of a coin coming up heads 15 times in a row. Improbable, but given enough flips it will happen eventually. A slightly more exotic explanation involves a supervoid, an enormous region of space with abnormally few galaxies lying between us and the CMB. Light passing through this void would lose a tiny amount of energy, appearing slightly cooler when it reaches us. Surveys have indeed found evidence of a large void in roughly the right location, but its size and depth may not be sufficient to fully account for the cold spot's temperature deficit. Scholars still argue whether the supervoid explanation is adequate, or whether something more fundamental is required. And then there is the truly exotic explanation. The cold spot, some theorists have suggested, could be the imprint of a collision between our universe and another one. In the context of eternal inflation, the idea that our observable universe is just one bubble in an infinite foam of bubble universes, collisions between adjacent bubbles would leave circular or roughly circular bruises on the CMB. The cold spot, with its roughly circular shape and anomalous temperature, fits the profile. If this explanation is correct, you're looking at evidence not just of a universe that existed before the Big Bang, but of other universes that exist alongside ours right now, pressing against the boundaries of our cosmic bubble like neighbours leaning against a shared fence. The cold spot is not the only anomaly. There is also the hemispherical asymmetry, a subtle but persistent observation that one half of the CMB sky has slightly larger temperature fluctuations than the other half. The Standard Model predicts that the fluctuation should be statistically identical in every direction. The universe should not have a preferred hemisphere, and yet, the data from multiple independent satellites consistently shows this lopsidedness, at a level of statistical significance that is hard to dismiss as a fluke. Some researchers have linked this to the possibility that the universe has a large-scale preferred direction, which would violate the cosmological principle, the foundational assumption that the universe looks the same in every direction on sufficiently large scales. Others have proposed that the asymmetry could be an artifact of our local motion through space, or a residual from the way the data was processed. The debate continues, politely but firmly. There is also the quadrupole-octupole alignment, a quirky feature in which the larger scale patterns in the CMB appear to be aligned with each other and with the plane of the solar system in a way that has no obvious explanation. This alignment has been nicknamed the axis of evil by cosmologists with a flair for drama, and while most researchers suspect it is a statistical coincidence or a systematic artifact, it remains unexplained and mildly irritating, like a painting that is slightly crooked and that nobody can quite straighten. What ties all of these anomalies together, and what gives them new relevance in the age of Webb, is the possibility that they are not random glitches in an otherwise perfect dataset, but are instead fingerprints. Fingerprints of something that existed before the CMB was released, before the universe became transparent, before the Big Bang itself. If the universe has a prehistory, whether it is Penrose's previous aeon, or a pre-bounce contraction phase, or a collision with a neighbouring bubble universe, that prehistory would leave marks. Faint, subtle, easily mistaken for noise, but marks nonetheless. And the CMB, being the oldest light we can observe, would be exactly where you would expect to find them. You breathe in slowly and imagine the microwave sky stretched above you like a faded tapestry. Its tiny imperfections, not flaws in the weaving, but messages from whatever came before, written in a language we're only just beginning to learn how to read. There is something else hiding in the early universe that does not add up, something you cannot see directly, but whose gravitational fingerprints are everywhere. Dark matter. The invisible scaffolding of the cosmos, the substance that makes up roughly 27% of the total energy content of the universe, and yet has never been directly detected in any laboratory on Earth. You have probably heard of it. It is one of those scientific concepts that has seeped into popular culture just enough that most people know it exists, without having any clear idea of what it actually is. Do not worry. Nobody else does either. Physicists know what dark matter does. They know how much of it there is. They know where it congregates and how it shapes the growth of structure in the universe. What they do not know is what it is made of, which, when you stop and think about it, is a fairly significant gap in our understanding of reality. What they do know is that dark matter forms halos, vast, roughly spherical clouds of invisible mass that surround galaxies and extend far beyond the visible stars and gas. These halos are the gravitational cradles in which galaxies are born. Without them, the ordinary matter, the hydrogen and helium that make up stars and planets and you, would never have collapsed into the dense clumps needed to form galaxies in the first place. The CMB fluctuations, those tiny temperature variations you just heard about, are the seeds of dark matter concentrations that grew over hundreds of millions of years into the halos that hosted the first galaxies. The process is hierarchical. Small halos form first, then merge with each other to build larger ones, like streams flowing into rivers flowing into a great ocean. The models predict this merging process in exquisite detail, and the predictions match observations of the large-scale structure of the universe with impressive accuracy. At least they used to. Webb's observations of the early universe are revealing dark matter halos that appear to be far more massive at high redshifts than the hierarchical merging model allows. The galaxies that should not exist are sitting inside dark matter structures that also should not exist, at least not so soon after the Big Bang. The halos are too big, they contain too much mass, and they seem to have assembled too quickly, as if the merging process that normally takes hundreds of millions of years was somehow fast-tracked or bypassed entirely. This is a problem that cuts deeper than the stellar mass budget crisis you heard about earlier, because dark matter is supposed to be the foundation. It is the thing that everything else is built on. If the stellar masses are too high, you can speculate about unusually efficient star formation, or exotic feedback mechanisms. But if the dark matter halos themselves are too large, there is nowhere to hide. You cannot form a massive dark matter halo faster than gravity allows, and gravity, despite being the weakest of the four fundamental forces, is extremely reliable. It does not suddenly become more efficient because the universe is young. It works at the same rate it always has. The only way to get a more massive halo sooner is to start the process earlier than the Big Bang. That is the implication that hangs in the air like smoke, and it connects directly to the bouncing and cycling cosmology models you heard about before. If dark matter existed in a previous phase of the universe, and if some of its structure survived the transition into our current phase, then the halos Webb is detecting might not have formed from scratch after the Big Bang. They might have inherited mass, gravitational influence, or structural seeds from whatever came before. The hierarchical merging timeline would not need to be violated because the merging process would have had a head start, building on foundations that were already in place when our universe began its expansion. Some theorists have gone further and proposed that dark matter itself might be a relic of the pre-Big Bang universe. If the Big Bang was a bounce or a phase transition rather than a creation event, the dark matter particles that pervade our cosmos might have been produced in the contraction phase that preceded the bounce, or in the dying stages of the previous aeon, or in the collision between brains in the ekpyrotic scenario. Their properties, their masses and interaction strengths might carry information about the physics of that previous epoch. Dark matter, in this view, is not just invisible scaffolding. It is a fossil record of a universe that no longer exists. A quirky detail that adds flavour to this speculation is that several dark matter candidates currently being investigated have properties that would be entirely consistent with a pre-Big Bang origin. Primordial black holes, which you will hear more about shortly, are one example. Certain types of axions, hypothetical ultra-light particles that are among the leading dark matter candidates, could in principle have been produced during a pre-bounce contraction phase. Even the much-discussed WIMPs, weakly interacting massive particles, could potentially have survived a cosmological bounce if the bounce temperature was not high enough to destroy them. The theoretical possibilities are surprisingly rich, and while none of them have been confirmed, none of them have been ruled out either. Scholars still argue whether the abundance of massive halos at high redshifts genuinely requires new physics, or whether adjustments to the existing Lambda CDM framework can accommodate the data. Some simulations have shown that tweaking parameters like the primordial power spectrum, the initial distribution of density fluctuations from which all structure grows, can produce more massive early halos without invoking anything exotic. Others argue that the required tweaks are so extreme that they effectively break the model's agreement with other observations, trading one problem for several new ones. You sink a little deeper and think about all that invisible mass out there, vast and silent, holding the galaxies in place like hands cupping water, and you wonder whether those hands were already there before the universe opened its eyes, whether the dark scaffolding of the cosmos was built by architects whose work predates everything you have ever known. And now, as if the galaxies were not enough and the dark matter halos were not enough, there are the black holes. Supermassive black holes specifically, the kind that sit at the centres of galaxies like enormous gravitational monarchs, pulling everything around them into orbits of devotion. The Milky Way has one. It is called Sagittarius A star, and it has a mass of about 4 million times that of the Sun. That is large by any human standard, but actually rather modest by supermassive black hole standards. Some galaxies host black holes with masses of billions of solar masses, engines of destruction and creation so powerful that the energy they release as they consume surrounding matter can outshine the entire galaxy in which they reside. These objects are well understood in the nearby universe. They grow over time, feeding on gas and dust and occasionally swallowing entire stars that wander too close. The process is called accretion, and it has a speed limit. The Eddington limit, named after the British astrophysicist Arthur Eddington, describes the maximum rate at which a black hole can consume matter before the radiation generated by the infalling material pushes back hard enough to shut off the flow. It is a self-regulating mechanism, like a drain that can only handle so much water before the pressure backs up. A black hole feeding at the Eddington limit doubles its mass in roughly 40 to 50 million years. That is fast by astronomical standards, but it means that growing a black hole from a small seed to 1 billion solar masses requires hundreds of millions of years of sustained, maximal feeding. And that timeline creates a problem in the early universe that is, if anything, even more severe than the galaxy formation problem. Webb, along with complementary observations from other facilities, has confirmed the existence of supermassive black holes at redshifts above 10, which places them within the first 500 million years after the Big Bang. Some of these objects have estimated masses of hundreds of millions of solar masses, and a few candidates approach the billion solar mass mark. The arithmetic is brutal. If you start with a stellar mass black hole, the kind that forms when a massive star collapses at the end of its life, typically around 10 to 100 solar masses, and feed it at the maximum Eddington rate continuously, without interruption from the moment the first stars formed, you still cannot reach 1 billion solar masses within 500 million years. You fall short, dramatically short. The black holes are too big, too soon, and no amount of aggressive feeding can make the numbers work. There are ways to ease the tension slightly. One approach is to start with a bigger seed. Instead of beginning with a stellar mass black hole, you begin with a so-called direct collapse black hole, formed when a massive cloud of primordial gas collapses directly into a black hole without ever forming a star first. These seeds could have masses of tens of thousands, or even hundreds of thousands of solar masses, which gives you a significant head start. The problem is that direct collapse requires very specific conditions: pristine gas with no heavy elements to facilitate cooling, a strong background of ultraviolet radiation to prevent the gas from fragmenting into smaller clumps, and a dark matter halo of just the right size. These conditions are possible in principle, but are expected to be rare, and the number of supermassive black holes Webb is finding at high redshifts seems to exceed the number of environments where direct collapse could plausibly have occurred. Another approach is super-Eddington accretion, the idea that black holes in the early universe somehow fed faster than the theoretical limit. This is not entirely implausible. The Eddington limit assumes a roughly spherical geometry of infalling material, and if the accretion flow is more complex, channeled along filaments, or occurring in bursts, brief episodes of super-Eddington feeding might be possible. Some simulations support this, showing black holes that can exceed the Eddington rate by factors of several for limited periods. But sustaining such rates over hundreds of millions of years is a different matter entirely, and the energy released by such vigorous accretion would likely blow away the very gas supply the black hole needs to keep growing. It is a self-defeating strategy, like trying to drink from a fire hose. A quirky observation that has added fuel to this debate involves a black hole discovered at a redshift of about 10.3, meaning it existed roughly 470 million years after the Big Bang. This particular object appeared to be significantly overmassive relative to its host galaxy, with a black hole-to-galaxy mass ratio far exceeding what is seen in the local universe. In nearby galaxies, the mass of the central black hole is typically about 0.1% of the total stellar mass of the galaxy. This ancient black hole appeared to account for a much larger fraction, as if the black hole had formed first and the galaxy had built up around it afterward. That reversal of the expected sequence, black hole first, galaxy second, has profound implications for how cosmic structure assembles, and it is one of those observations that makes theorists stare at whiteboards for uncomfortably long periods. Scholars still argue whether these early supermassive black holes represent a genuine crisis for the Standard Model, or whether creative combinations of large seeds, super Eddington accretion, and early mergers can salvage the conventional picture. The debate is active, vigorous, and nowhere near settled. But the trend is unmistakable. Just as with the galaxies and the dark matter halos, the black holes are bigger than they should be, older than they should be, and more numerous than they should be. And the quiet question continues to build. If they did not have time to grow this large after the Big Bang, did they start growing before it? You picture a black hole in the darkness, not as a terrifying maw, but as something ancient and patient, something that might have been sitting in the fabric of reality before reality as you know it even began, and the thought is oddly peaceful. The idea of black holes that predate the Big Bang sounds like it belongs in a fever dream, but it has a name, a theoretical framework, and a growing number of supporters. They're called primordial black holes, and they represent one of the most fascinating and contentious ideas in modern cosmology. Unlike the black holes you're accustomed to hearing about, the ones that form when massive stars collapse at the end of their lives, primordial black holes would have formed from the fabric of space-time itself, born not from stellar death, but from the extreme conditions of the very early universe, or possibly from conditions that existed before it. The concept is not new. Stephen Hawking and Bernard Carr proposed the existence of primordial black holes in the 1970s, suggesting that density fluctuations in the first moments after the Big Bang could have been large enough in some regions to cause matter to collapse directly into black holes without going through the intermediate step of forming stars. The idea was elegant but somewhat academic at the time, because there was no observational evidence for or against it. Primordial black holes were a theoretical possibility, like a room in a house that you know the blueprints allow for, but that you have never actually entered. They remained in the background of cosmological thinking for decades, occasionally invoked in speculative papers, but never quite making it to the centre of the conversation. Webb has changed that. The discovery of supermassive black holes at extreme redshifts, black holes that cannot be explained by conventional growth from stellar mass seeds, has revived interest in primordial black holes with a vigour that would have been unimaginable just 10 years ago. If some black holes did not form from stars but were instead present in the universe from its very earliest moments, then the timeline problem disappears. They did not need to grow from small seeds over hundreds of millions of years. They were already large, already massive, already sitting at the centres of nascent dark matter halos, ready to anchor the formation of the galaxies that Webb is detecting. The mechanism by which primordial black holes could have formed depends on which model of the early universe you favour. In the standard inflationary picture, density perturbations during inflation could have produced regions dense enough to collapse into black holes immediately after inflation ended. The mass of these primordial black holes would depend on the scale of the perturbation and the time at which they formed, with some models predicting a wide spectrum of masses ranging from tiny, subatomic black holes that would have evaporated long ago through Hawking radiation, to enormous objects with thousands or millions of solar masses. In bouncing cosmology models, primordial black holes could have formed during the contraction phase that preceded the bounce, when the density of the universe was increasing and conditions for gravitational collapse were naturally favourable. In Penrose's conformal cyclic cosmology, the supermassive black holes of the previous aeon would have evaporated through Hawking radiation, but the energy they released in doing so could have seeded density enhancements in the new aeon that collapsed into new primordial black holes shortly after the transition. Each of these scenarios makes different predictions about the mass distribution, spatial clustering, and abundance of primordial black holes, and distinguishing between them is one of the great observational challenges of the coming decades. but what they all share is the implication that at least some of the black holes in our universe were not built by the universe. They were inherited, handed down from a previous epoch, a previous phase, or a previous set of physical conditions that left its mark on the cosmos in the form of gravitational seeds planted before the garden of the observable universe was even sown. A quirky and rather charming detail in the history of primordial black hole research involves the persistent suggestion that they might constitute some or all of the dark matter. If primordial black holes exist in sufficient numbers and with the right mass range, they could account for the gravitational effects attributed to dark matter without requiring any new fundamental particle. This idea has gone in and out of fashion multiple times, constrained by various observations but never entirely killed off. Each time it seems to be ruled out in one mass range, theorists find a window in another range where it remains viable. It is the cosmological equivalent of a whack-a-mole game, and the mole is surprisingly resilient. Scholars still argue whether primordial black holes are a genuine solution to the early universe puzzles, or whether they simply replace one mystery with another. After all, explaining the origin of supermassive black holes by invoking primordial black holes only pushes the question back a step. You still need to explain how the primordial black holes formed, and that requires understanding the physics of the very early universe, or the pre-Big Bang universe, with a precision that current theory does not provide. But the fact that the hypothesis exists, that it is taken seriously by mainstream researchers, and that it naturally connects to multiple independent lines of evidence, from Webb's impossible galaxies to the dark matter problem to the CMB anomalies, gives it a weight that purely speculative ideas rarely achieve. You think about Hawking, who proposed these objects half a century ago, long before any telescope could have seen the evidence that now points in their direction. You think about seeds planted in darkness, invisible and patient, waiting for gravity to do its slow, inevitable work. And you realize that the universe might be full of things that were there from the very start, or from before the start, ancient beyond measure, hidden in plain sight behind the veil of dark matter and deep time. You're deep enough into the dark now, both the darkness of the room around you and the darkness of the questions being raised, that it seems like a good time to go even further, because if the ideas you have encountered so far feel strange, what comes next makes them look almost conservative. This is the territory of string theory, the multiverse, and the possibility that our entire universe is just one thin sheet in an infinite stack of realities, and that Webb might, just might, be detecting the faintest shadows of what lies beyond. String theory is one of those concepts that nearly everyone has heard of, and almost nobody fully understands, including, if you press them at the right moment, a fair number of the physicists who work on it. The basic premise, distilled to its simplest essence, is that the fundamental building blocks of the universe are not point-like particles, but tiny, one-dimensional vibrating strings of energy. The different ways these strings vibrate produce different particles, much as different vibrations of a guitar string produce different notes. An electron is a string vibrating one way, a quark is a string vibrating another. Gravity, electromagnetism, the nuclear forces, all of them emerge from the harmonics of these impossibly small entities, which operate at a scale roughly a billion times smaller than a proton. The mathematical framework of string theory is extraordinarily elegant, and it achieves something that no other theory has managed. It naturally incorporates gravity into a quantum framework, unifying all four fundamental forces into a single coherent description. This is the holy grail of theoretical physics, the theory of everything that Einstein spent the last 3 decades of his life searching for without success. String theory, in principle, provides it. There's just one small complication, actually several rather large complications. First, string theory requires extra dimensions, not the 3 spatial dimensions and 1 time dimension that you experience in everyday life, but 10 or 11 dimensions in total, depending on which version of the theory you prefer. The extra dimensions are assumed to be compactified, curled up so tightly at the Planck scale that they are undetectable by any experiment we can currently perform. This is not inherently absurd. A garden hose viewed from a great distance appears to be a one-dimensional line, but up close you can see that it has a circular cross-section, a second dimension that was hidden by distance. The extra dimensions of string theory might work the same way, invisible at our scale but profoundly influential at the quantum level. Second, string theory does not produce a single unique solution. It produces a landscape of possible solutions, estimated at around 10 to the power of 500 different configurations, each corresponding to a different possible universe with different physical constants, different particle masses, different numbers of large dimensions, and different laws of physics. This is not a small number. It is a number so incomprehensibly large that writing it out in full would require more digits than there are atoms in the observable universe. And each of those solutions, each point in the landscape, could in principle correspond to a real universe. This is where the multiverse enters. If string theory is correct and the landscape is real, then the question is not which solution describes our universe. The question is why our universe corresponds to one particular solution rather than any of the others. One answer, and it is the answer that drives some physicists to despair and others to excitement, is that all of them are real. Every solution in the landscape is realized somewhere, in some bubble universe nucleating out of a false vacuum in an eternally inflating cosmos, each one with its own laws of physics, its own particles, its own history, completely disconnected from the others except, and this is the crucial except, at the boundaries. Because string theory also gives us brains. Short for membranes, brains are higher dimensional objects that exist within the full dimensional space of string theory. Our entire observable universe, in some models, is a 3-dimensional brain floating in a higher dimensional bulk, like a sheet of paper suspended in a room. And there could be other brains nearby, other universes, separated from ours by a distance in the extra dimensions that might be astonishingly small. Remember the ekpyrotic model from earlier, the one where the Big Bang is caused by 2 brains colliding. That model lives here, in this framework, and it predicts that the collision between brains would leave signatures, patterns of energy and density that could influence the structure of the resulting universe. Scholars still argue whether string theory can ever be tested in any meaningful sense, and the debate is one of the most polarizing in all of modern physics. Critics point out that a theory with 10 to the 500 solutions can predict essentially anything, which means it predicts nothing. Supporters counter that the mathematical consistency of the framework is itself a powerful form of evidence, and that specific predictions about gravitational waves, about the CMB, about the properties of black holes, are gradually becoming testable. The argument has been running for decades and shows no signs of resolution, which is either a sign that the question is genuinely difficult, or that physicists are genuinely stubborn. Probably both. A quirky footnote is that Edward Witten, widely regarded as the most brilliant living mathematical physicist, once described string theory as a piece of 21st century physics that fell by accident into the 20th century. The implication being that we stumbled onto the theory before we had the tools, experimental or conceptual, to fully understand it. Webb may not be that tool, but it might be providing the first observational hints that the multiverse, or something like it, has left marks on our cosmos. Those impossible galaxies, those structures too old for our universe, might be echoes of a neighbouring brain, artifacts of a collision that happened in dimensions we cannot perceive, fingerprints pressed into our reality by hands reaching from beyond. You let that settle over you like a blanket made of questions, and the darkness in the room feels vast, not threatening but open, as if the walls have dissolved and you're lying on your brain, your little sheet of reality, with infinity stacked above and below you in directions you will never see. All of these ideas, the bouncing universe, the cyclic aeons, the colliding brains, the primordial black hole seeded from a previous existence, they all share one thing in common. They all challenge the standard inflationary model, the reigning explanation for how the universe got to be the way it is in its earliest moments. And Webb's impossible galaxies have reignited a debate about inflation that has been smouldering quietly in the background of cosmology for years, but is now threatening to become a full blaze. Inflation, if you have not encountered it in detail before, is the idea that the universe underwent a period of exponentially rapid expansion in the first tiny fraction of a second after the Big Bang. We touched on it earlier, but it deserves a closer look now because understanding what inflation does and does not explain is essential to understanding why the current crisis matters. The theory was proposed in 1981 by Alan Guth, a young physicist who was trying to solve several puzzling features of the observed universe that the basic Big Bang model could not account for. The first puzzle was the horizon problem. The CMB is remarkably uniform in temperature across the entire sky, but regions on opposite sides of the sky are so far apart that light has not had time to travel between them since the Big Bang. They have never been in causal contact. They have no way of knowing about each other, and yet their temperatures agree to extraordinary precision. It is as if two people on opposite sides of the Earth, who have never communicated, both decided to set their thermostats to exactly the same temperature down to the 5th decimal place. Without some mechanism to explain this uniformity, it is an absurd coincidence. The second puzzle was the flatness problem. The geometry of the universe appears to be very nearly flat, meaning that parallel lines remain parallel over cosmic distances, and the angles of a triangle add up to 180 degrees. But in the standard Big Bang model, flatness is an unstable condition. Even a tiny deviation from perfect flatness in the early universe would have been amplified over billions of years into a dramatically curved cosmos. The fact that the universe is still so close to flat after 13.8 billion years implies that it was flat to an almost miraculous degree of precision at the very beginning, fine-tuned to 1 part in 10 to the 60. That level of fine-tuning makes physicists deeply uncomfortable because it looks less like a natural outcome and more like someone deliberately setting the initial conditions. Inflation solved both problems beautifully. By expanding the universe by a factor of at least 10 to the 26 in a tiny fraction of a second, inflation took a small, causally connected patch of space and stretched it to enormous size. The uniformity of the CMB is explained because the entire observable universe was once a single, tiny region that had plenty of time to reach thermal equilibrium before inflation blew it up. The flatness is explained because inflation stretches any curvature to imperceptibility, the same way inflating a balloon makes its surface appear flat to an ant standing on it. Inflation also predicted specific statistical properties of the CMB fluctuations, predictions that were spectacularly confirmed by the WMAP and Planck satellites. It was, by almost any measure, one of the great theoretical triumphs of 20th century physics. But inflation has problems of its own, and they are not small ones. The most fundamental is that nobody knows what caused it. Inflation requires a scalar field, the inflaton, with very specific properties, and this field has never been detected or identified with any known particle. It is at present a purely hypothetical entity invented to make the theory work. Scholars still argue whether invoking an undetected field to solve cosmological puzzles represents genuine explanatory progress or simply replaces one set of mysteries with another. The debate has a surprisingly sharp edge for an argument between people who are ostensibly on the same side. There is also the measure problem. Inflation, once it starts, tends to be eternal. The inflaton field does not stop inflating everywhere at once. Instead, it decays in some regions, creating bubble universes like ours, while continuing to inflate in others, spawning an infinite number of bubbles in an ever-expanding cosmic foam. This is eternal inflation, and it leads directly to the multiverse. The problem is that in an infinite multiverse, everything that can happen does happen an infinite number of times, which makes it impossible to assign meaningful probabilities to any observation. You cannot say that our universe is typical or atypical, because there is no well-defined way to compare infinite sets. This is not a minor technical issue. It strikes at the heart of whether inflation can make testable predictions at all, and some of its most prominent critics, including Paul Steinhardt, who was one of the original architects of inflationary theory, have argued that the theory has become unfalsifiable and therefore unscientific. Webb's data pours fuel on these flames. If the standard inflationary model predicts a specific timeline for structure formation, and that timeline is being violated by the data, then either inflation needs to be modified or replaced. A quirky irony here is that Steinhardt, who helped build inflation, is now one of the leading proponents of the bouncing cosmology that could replace it. He has spent years developing the ekpyrotic model as an alternative, arguing that it explains everything inflation explains without the baggage of eternal inflation and the multiverse. His colleagues have responded with a mixture of admiration and exasperation, the way you might feel about a friend who builds a beautiful house and then spends the rest of their life trying to tear it down. You stare at the ceiling, or rather through it, into the conceptual void where these theories wrestle with each other, and you feel the strange comfort of knowing that even the smartest people alive do not agree on how the universe began. It means the story is still being written. It means there are still chapters left to discover, and somewhere in those unwritten chapters, the answer to what Webb has found might finally make everything click into place. By now you have been swimming in some of the deepest waters that modern cosmology has to offer, and it might be worth pausing for a moment, taking a slow breath in this gentle dark, and asking a deceptively simple question. What does it actually mean to say that something is older than the Big Bang? Because the phrase has been floating through this conversation like a ghost, and if you look at it too directly, it starts to shimmer and dissolve into something much more complicated than the words suggest. The problem begins with time. You think you understand time. Everybody thinks they understand time. It moves forward. One thing happens, then another thing happens. Yesterday was before today. Tomorrow will come after. Your alarm goes off. You make coffee. You exist in a sequence of events that unfolds in a single, irreversible direction. This intuitive understanding of time works perfectly well in everyday life, and it has served humanity without complaint for the entirety of its existence. But at the scale of the cosmos, and particularly at the extremes of the very early universe, this intuition fails. Quietly, completely, and without apology. In general relativity, time is not a fixed background against which events play out. Time is part of the fabric of space-time, and it is shaped by the distribution of matter and energy. Massive objects warp time. A clock on the surface of the Earth ticks slightly slower than a clock in orbit, a fact that GPS satellites have to correct for every day, or the whole system would drift into uselessness within hours. Near a black hole, time slows to a crawl. At the singularity inside a black hole, time, as far as the equations can tell, stops altogether. Time is not a river flowing at a constant rate. It is more like a landscape, with hills and valleys and places where the terrain becomes so extreme that the concept of forward motion loses meaning. At the Big Bang singularity, according to general relativity, time begins. Not in the sense that a clock starts ticking in an already existing void, but in the sense that time itself comes into existence along with space and matter and energy. There is no moment before the Big Bang because there are no moments. The question, what happened before the Big Bang, is, in this strict framework, like asking what is south of the South Pole. You can walk in any direction from the South Pole and you will be heading north. The coordinate system simply does not extend beyond that point. The Big Bang is the South Pole of time. But here is where it gets interesting. General relativity is not the final word. It is a classical theory, magnificently successful at large scales, but it breaks down precisely at the conditions where you most need it to work, at the singularity itself. The equations produce infinities, and infinities in physics are almost always a sign that the theory has reached its limits, and something deeper is required. That something deeper is quantum gravity, the still unfinished theory that would merge general relativity with quantum mechanics. And in nearly every approach to quantum gravity, whether it is loop quantum gravity, string theory, or something else entirely, the singularity is resolved. It is smoothed out, replaced by something finite, and in being replaced, the absolute beginning of time is replaced as well. In loop quantum cosmology, as you heard earlier, the singularity becomes a bounce. Time does not begin at the bang. It continues through it from a prior contraction phase. In Penrose's conformal cyclic cosmology, time is redefined at the boundary between aeons, with the infinite future of one aeon becoming the zero time origin of the next through a conformal rescaling. In the ekpyrotic model, time exists in the higher dimensional bulk, even when the branes are between collisions. In each of these frameworks, before the Big Bang is not a meaningless phrase. It refers to a genuine epoch of physical reality, a period in which events occurred, processes unfolded, and structures could form. This is what older than the Big Bang actually means in the context of Webb's discoveries. It does not mean that someone has found a galaxy with a timestamp reading made in the previous universe. It means that the structures Webb is detecting appear to require more time to form than has elapsed since the Big Bang, and that the most natural explanation for this discrepancy, if the data holds up, is that the formation process began in a phase of reality that preceded the hot, dense state we call the origin of our universe. The galaxies are not older than time, they are older than our time. They belong potentially to a chapter of cosmic history that the standard model does not include, a chapter that begins before page 1. Scholars still argue whether the concept of before the Big Bang is physically meaningful or merely a mathematical artifact of theories that have not yet been tested. The philosophical stakes are enormous. If time extends infinitely into the past, then the universe has no beginning, and the question of what caused it to exist loses much of its force. If time is cyclic, then every ending is a beginning and every beginning is an ending, and the entire notion of a first cause becomes slippery and strange. If time is emergent, arising from deeper quantum processes that are themselves timeless, then the question of before is not answered, but dissolved, revealed to be a question that only makes sense within the framework it is trying to transcend. A quirky thought experiment that physicists sometimes use to illustrate the problem involves imagining a universe in which time has 2 dimensions instead of 1. In such a universe, the concept of before would branch like a tree, with multiple paths leading to a single present, and the question, what happened before X, would have infinitely many answers depending on which direction in time you looked. It is absurd, probably, but it serves as a useful reminder that our intuitive sense of time is not a law of nature. It is a habit of mind shaped by evolution and experience, and the universe is under no obligation to conform to it. You feel time softening around you now, the boundaries of the day blurring, the distance between this moment and sleep narrowing, and you think about a cosmos where before and after are not walls but doors, and every door opens onto another room that goes back further than you ever imagined. The data is in, the theories are on the table, and now the most human part of the story unfolds, the part where people argue. Because science is not a smooth conveyor belt moving calmly from question to answer. It is a room full of brilliant, passionate, occasionally stubborn individuals who have spent their careers building models of reality, and when someone walks in with evidence that those models might be incomplete, the reactions range from gracious curiosity to something that looks a lot like grief. The astronomical community's response to Webb's early universe findings has been fascinating to watch, not because it is unusual for scientists to disagree, but because the disagreement reveals so clearly the fault lines that run through modern cosmology. On one side, you have the conservatives, the researchers, who have devoted decades to the Lambda CDM model, and who believe, with considerable justification, that it is the most successful cosmological framework ever constructed. These scientists look at Webb's impossible galaxies and see puzzles, certainly, but puzzles that can be solved within the existing paradigm. They point to the uncertainties in photometric redshifts, the assumptions baked into stellar mass estimates, the possibility that exotic but not revolutionary physical processes could explain the data. They counsel patience. They remind their colleagues that extraordinary claims require extraordinary evidence, and that the history of astronomy is littered with anomalies that seemed earth-shattering at first, and turned out to have mundane explanations. On the other side, you have the revolutionaries. These are the physicists and cosmologists who have long harboured doubts about aspects of the Standard Model, who've been developing alternative frameworks in relative obscurity, and who now see Webb's data as potential vindication. For them, the impossible galaxies are not glitches to be explained away. They are signals, harbingers of a paradigm shift that has been building for years and is now finally reaching critical mass. They publish papers with titles that, by the restrained standards of academic prose, practically vibrate with excitement. They give talks at conferences where the Q&A sessions run twice as long as scheduled. They update their theoretical predictions and point to the growing list of observations that their models anticipated, while the Standard Model did not. Between these two camps lies a vast middle ground occupied by researchers who are genuinely uncertain. These are the scientists who find the data compelling, but the alternative theories unproven, who acknowledge that Lambda CDM is under strain but are not yet ready to abandon it for something that might be worse. They write careful papers hedged with caveats. They run simulations testing whether modified versions of the Standard Model can accommodate the data without breaking its agreement with other observations. They organise workshops with titles like Tensions in Cosmology and New Challenges for Galaxy Formation Theory, which sounds dry but is actually the academic equivalent of a summit meeting during a crisis. A quirky sociological detail about these debates is the role played by preprint servers, particularly Archive, where most physics and astronomy papers are posted before formal peer review. In the age of Webb, Archive has become a battleground. New observational results appear, and within days, sometimes hours, theoretical responses are posted. Rebuttals follow. Counter-rebuttals follow those. The pace of the discourse is unprecedented, driven partly by the significance of the findings and partly by the very human desire to be the first to explain what is going on. One researcher described the atmosphere as exhilarating and exhausting, which is probably the most honest summary anyone has offered. The debate has also spilled beyond the walls of academia into the broader public sphere, where the nuances tend to get smoothed out into more dramatic narratives. Headlines declare that James Webb has disproved the Big Bang, or that the universe is twice as old as we thought, neither of which is accurate, at least not yet. The Big Bang has not been disproved. The core observations that support it, the expansion of the universe, the cosmic microwave background, the abundance of light elements, remain robust. What is under challenge is not the Big Bang itself, but the specific timeline and mechanisms of the Standard Model, the details of how the universe evolved in its first few 100 million years. The distinction matters, but it is subtle enough that it frequently gets lost in translation. Scholars still argue whether the current moment represents a genuine crisis in cosmology, or merely a period of healthy tension that will ultimately strengthen the Standard Model. The word crisis itself is contentious. Some researchers embrace it, arguing that only by acknowledging the severity of the discrepancies can the field mobilize the resources and creativity needed to resolve them. Others resist it, warning that premature declarations of crisis can distort research priorities and attract the wrong kind of attention, both from sensationalist media and from fringe theorists eager to hijack legitimate scientific uncertainty for their own purposes. The politics of knowledge production are never simple, and cosmology, for all its cosmic grandeur, is subject to the same institutional pressures and human dynamics as any other field. What is undeniable is that the conversation has shifted. 5 years ago, suggesting that structures in the universe might predate the Big Bang would have earned you polite nods and quiet skepticism at most cosmology conferences. Today, the same suggestion prompts vigorous discussion, detailed counter-arguments, and, crucially, proposals for new observations that could test the idea. That shift, from dismissal to engagement, is perhaps the clearest sign that Webb's data has done something genuinely important. It has not answered the question of what came before the Big Bang, but it has made the question scientifically respectable in a way that it was not before. You lie in the dark and listen to the echoes of that debate, the careful voices and the excited ones, the cautious papers and the bold hypotheses, and you realize that you are living through a moment that future historians of science will write about. A moment when the boundary of human knowledge shivered, and the map of the universe developed a new, unexplored edge. The arguments will continue, as arguments in science always do, for years and possibly decades. But the telescope is not waiting for consensus. Webb is still up there, orbiting its quiet Lagrange point, its golden mirror drinking in ancient photons with the patience of something that has no deadlines and no opinions. And the next round of observations is already being planned, designed specifically to test the most radical implications of what has been found so far. The first priority is spectroscopic confirmation. Many of the impossible galaxy candidates identified in Webb's early surveys were detected using photometry, which measures the brightness of an object across several broad wavelength bands and uses the pattern of brightness to estimate the redshift. Photometric redshifts are powerful but imprecise, and they can occasionally be fooled. A dusty galaxy at moderate redshift can, under certain conditions, mimic the spectral signature of a pristine galaxy at extreme redshift. The colours look similar even though the objects are fundamentally different. This ambiguity has been a persistent source of caution in the debate, with skeptics arguing that some fraction of the impossible galaxies might turn out to be imposters, ordinary objects masquerading as extraordinary ones. Spectroscopic confirmation eliminates this ambiguity. By splitting the light of each object into a detailed spectrum and identifying specific emission or absorption lines, astronomers can pin down the redshift with much greater precision and simultaneously determine the chemical composition, star formation rate, and physical conditions within the galaxy. Webb's near-infrared spectrograph, or NIR spec, is capable of doing this for the most distant objects ever observed, and dedicated spectroscopic follow-up programs are already underway. The results so far have been both reassuring and alarming. reassuring because the spectroscopic redshifts have confirmed that the vast majority of candidates are indeed at the extreme distances their photometry suggested. Alarming because confirmation means the problem is real and is not going to be wished away by better data reduction. The second priority is understanding the stellar populations within these early galaxies in more detail. Webb's Mid-Infrared Instrument, or MIRI, observes at longer wavelengths than NeoSpec and is sensitive to the light emitted by older, cooler stars, the kind that take hundreds of millions of years to evolve to their current state. If MIRI detects a significant population of evolved stars in galaxies at redshift above 10, the implications would be profound. It would mean that star formation in those galaxies began even earlier than the galaxy's observed epoch, pushing the required formation time back toward, or beyond, the Big Bang itself. Several MIRI observation programs targeting the most extreme high redshift candidates have been approved, and the cosmological community is watching with the kind of focused intensity usually reserved for election nights and penalty shootouts. A third avenue of investigation involves gravitational waves. The next generation of gravitational wave detectors, including the space-based LISA mission planned for launch in the mid-2030s, will be sensitive to the mergers of massive black holes in the early universe. If the supermassive black holes Webb has found at high redshifts grew through a series of mergers, those mergers would have produced gravitational waves that are still propagating through the cosmos. Detecting them would provide an independent confirmation of the black hole's existence and, crucially, information about their masses and merger histories that could distinguish between conventional growth models and more exotic scenarios involving primordial black holes or pre-Big Bang seeds. Scholars still argue whether LISA's sensitivity will be sufficient to reach the most distant merger events, but the theoretical forecasts are encouraging. There's also the tantalizing possibility of detecting direct signatures of a pre-Big Bang phase in the CMB, next-generation CMB experiments, including the Simons Observatory, currently under construction in Chile, and the proposed CMBS-4 project, will map the polarization of the cosmic microwave background with unprecedented precision. Polarization patterns encode information about gravitational waves generated in the very early universe and different models of the early universe. Inflation, bouncing cosmology, conformal cyclic cosmology predict different polarization signatures. If the bounce or the cyclic transition left its mark on the primordial gravitational wave background, these experiments might be able to detect it. The signal would be subtle, buried beneath foreground contamination from our own galaxy and the integrated effects of billions of years of cosmic evolution. But the technology is advancing rapidly, and what was impossible a decade ago is becoming merely very difficult. A quirky and hopeful detail in all of this is the role of artificial intelligence in analysing the torrent of data these instruments will produce. Machine learning algorithms are already being used to classify galaxies in Webb's deep field images, to identify candidate high redshift objects, and to model the spectral energy distributions of distant sources. As the datasets grow larger and the questions become more nuanced, AI is expected to play an increasingly central role in the discovery process, sifting through terabytes of information to find the subtle patterns that human eyes might miss. One research team has already used a neural network to identify previously overlooked high redshift candidates in existing Webb data, finding objects that the initial human-led analysis had classified as noise. The machines are learning to see what we cannot, and in a field where the most important signals are the faintest ones, that is a significant advantage. You picture the telescope out there in the cold, turning its mirror toward the next patch of ancient sky, and you picture the detectors on Earth, waiting for the faintest tremor of a gravitational wave, and the CMB observatories on mountaintops, listening for the whisper of a universe that might have existed before this one. The search is not over. It is barely beginning. And the tools being built to continue it are some of the most extraordinary machines humanity has ever conceived, each one designed to ask the same question in a different language. Was something there before the beginning? And if so, what was it? So here you are, at the edge of everything. Not the edge of the universe, because the universe may not have one, but the edge of what is known. The boundary between the mapped and the unmapped, the explained and the unexplained, the comfortable story and the unsettling possibility that the story is much, much bigger than anyone suspected. You've travelled a long way tonight, from the golden mirror of a telescope floating in the cold of deep space, through the impossible galaxies it found in the infant cosmos, past the straining models and the arguing physicists, through bouncing universes and cycling eons and vibrating strings and colliding brains, all the way to this quiet moment where you lie in the dark and wonder what it all means. And maybe that is the most honest question to end on. Not what the data shows, not what the theories predict, not which model of the early universe will ultimately prevail, but what it means. What does it mean for you, a single conscious being on a small rocky planet orbiting an ordinary star in an unremarkable galaxy, to learn that the universe you inhabit might not be the first, that the Big Bang, which you were taught was the ultimate origin, the moment when everything began, might itself have been preceded by something vast and ancient and filled with its own stars and galaxies and perhaps its own forms of wonder. It means, at the very least, that the story is not finished. That is the thing about science that is easiest to forget and most important to remember. It is not a collection of facts carved into stone. It is a process, a living, breathing, occasionally stumbling process of asking questions and following the evidence wherever it leads, even when it leads to places that make the questioners uncomfortable. The Big Bang model is not wrong in the way that flat Earth theory is wrong. It is incomplete in the way that all our best theories have always been incomplete, capturing a piece of reality with extraordinary precision while leaving room, at the edges, for something deeper and stranger to emerge. Newton was not wrong about gravity. He was incomplete. Einstein filled in what Newton missed, and someday, someone will fill in what Einstein missed, and the process will continue for as long as there are minds curious enough to look at the sky and ask why. What Webb has done, in its quiet, methodical, golden way, is widen the crack at the edge of the map. It has shown us that the earliest moments of the universe were not the barren, empty epoch we imagined, but a place already teeming with structure and complexity. It has forced us to confront the possibility that our origin story has a prologue, one we have not yet read, written in a language we're only beginning to decipher. Whether that prologue describes a previous universe, a bouncing cosmos, a cyclic aeon, or something entirely beyond our current theoretical imagination, we do not yet know. We may not know for decades. But the question is now on the table, and it is not going away. A mainstream historical fact worth holding on to here is that every major revolution in cosmology has followed the same pattern. An observation is made that does not fit the existing model. The community resists, investigates, argues, and eventually, if the evidence is strong enough, adapts. The Copernican revolution took over a century. The acceptance of an expanding universe took decades. The discovery of dark energy, which showed that the expansion is accelerating, went from heresy to Nobel Prize in less than 15 years. The pace of change is accelerating along with the cosmos itself, and Webb's findings have all the hallmarks of the next great shift. Scholars still argue whether we are at the beginning of that shift or merely at the point where the first cracks are appearing in the dam, but the water is rising either way. A quirky and rather beautiful thought to carry with you as you drift is that if the universe is cyclic, if aeons give way to aeons in an infinite procession, then in some deep sense nothing is ever truly lost. The stars that burned in a previous cosmos scattered their elements into the void, and those elements, transformed by the transition, became the raw material of new stars in a new cosmos. You're made of atoms that were forged in stellar furnaces, and if the cyclic models are right, the ancestry of those atoms may stretch back not just to the first stars of our universe, but to the last stars of one that came before. You are perhaps older than you think. Much older. Older than the Big Bang. Older than the origin story, made of recycled stardust from a cosmos that dreamed and died, and in dying gave its substance to you. The telescope keeps watching. The data keeps arriving. The questions keep multiplying. And somewhere out there, in the infrared glow of the most ancient light, the answer is waiting with the patience of something that has been waiting a very, very long time. Now the room around you is soft. The sounds of the world outside, the hum of traffic or the whisper of wind or the gentle ticking of a clock, they're fading to the edges of your awareness, becoming part of the background, blending into the quiet static of the cosmic microwave background itself. Your breath is slowing. Your thoughts are loosening, untethering from the sharp edges of facts and theories and drifting into something gentler. The galaxies you heard about tonight, those impossible, luminous, ancient objects, they are still out there. They will be there tomorrow. They will be there next week. They do not need you to stay awake for them. They have been shining for longer than you can comprehend, and they will continue long after you have slipped into sleep. So let them shine. Let the telescope do its work. Let the physicists argue and the theorists dream, and the data accumulate in its slow, patient way. You have done your part tonight. You listened. You wondered. You let your mind stretch to the edges of the knowable and peer, just for a moment, into the dark beyond. That is enough. That is more than enough. The light from the oldest galaxies is still falling through space, and it will be falling when you wake. The universe is still expanding, still cooling, still evolving, still revealing itself one photon at a time. And you, warm beneath your blankets, breathing slowly, eyes heavy, a part of it. A small part, yes. A brief part, certainly. But a part that can look up and ask questions that the universe itself cannot answer, and there is something wonderful in that. Something worth holding gently as you let go of the day and drift, slowly, softly, inevitably, into the warm, welcoming dark of sleep. The stars will keep your place. Sweet dreams.